So in the previous two episodes, I told you about what happens when we change objective coefficients in linear programming, one at a time, right? And then if we found out, right, that if we change one objective coefficient within the range of optimality, and all other coefficients remain the same, the old optimal solution is still optimal, and we can then find exactly the new optimal objective function value. So we know this remains optimal, and we will find what's the new optimal objective function value after we change one of the coefficients in the objective. I also showed you the examples where if you change one of those coefficients outside of the range of optimality, right? So maybe you change it above 450 or below 300, this first coefficient, and of course, by analogy, we could have done the same for the second coefficient, right? We change it above 350, this 300, the second coefficient, or we decrease it such that it becomes less than 233. And then we know the optimal solution, the old optimal solution, this one, might no longer be optimal. So if you were to resolve this problem, you would find maybe another optimal solution, but we could still find something about the optimal objective function value. We couldn't find it exactly, but we could find in all cases what's the lower bound on the objective function value, and sometimes also what's the upper bound. Notice that this is true whenever the objective is maximization and we make changes in the coefficients, we can always find the lower bound. If the objective was minimization, we could always find the upper bound of the objective function value. Now, in this episode, I want to show you what happens when you change more than one objective coefficient. So again, we're going to use this 100% rule for objective coefficients. There's another 100% rule for constraints. But for now, for objective coefficients, if we change multiple objective function coefficients, right? So like, for example, we change this 350 and also we change 300, but we keep all the other numbers in the constraints in particular, right? All the other numbers in the model, we keep them the same. The old optimal solution will still be optimal if the percentage, the total percentage change of allowable changes does not exceed 100. So I want to show you now examples of how this works. So here is the first example. What if objective coefficient for Aqua Spa increases to 400, right? It was 350, now it is 400. So it increases by 50. And at the same time, objective coefficient for Hydroluxes for the second decision variable decreases to 280. It was 300, now it becomes 280, so it decreases by 20. What happens then? Well, first thing to observe is 400, right, the first coefficient, is within the range of optimality, right, 300 to 450, right, this range, it is within. And the second coefficient, and 280, is within the range of optimality, which is 233.333 to 350, right? Again, we are somewhere between those numbers. Even if we were at the limit, we would still be within the range, right? So on their own, each of those changes does not, if we just changed first coefficient to 400, the optimal solution would remain the same. If we just change the second coefficient to 280, the optimal solution would remain the same, right? So, but if we change both of them, right? If we change both of them, can we say anything, right? So again, by analogy, I could say, just to be complete, increase here by 50 is less than or equal allowable increase, which is equal to 100. And same thing here, right? Increase by, this is decrease by 20 is less than or equal allowable decrease, which is 66.67 here, right? This number. So, right, so each of those changes separately, if we were to do them, would not change the optimal solution. The old optimal solution would still remain the same. However, changing both, right? When we change both, just finding that they are within the range is not sufficient, right, to decide if the old optimal solution will still be optimal, right? Why? Because we changed more than one coefficient, right? If we change more than one coefficient, no guarantees, right? However, we have this 100% rule. So applying the 100% rule for objective coefficients, what we need to do is calculate what's the total percentage change. And the total percentage change is basically calculated as all increase divided by allowable increase. Notice we've done one increase, 50, and another decrease. So we need to add increase over allowable increase for the first coefficient, plus, right, we need to add decrease for the second coefficient divided by allowable decrease, right? So just two changes. If there were more changes, right, if I had 100 variables and I would change 5 coefficients, I would have to just add all the changes relatively to allowable increases or decreases. And so let's put the numbers here. This will be 50 over 100 plus, right, this is 20 over 66.67. So 20 over 66.67. Right? And if you do the calculation, so obviously this is 0.5, and this happens to be almost, right, it's 0.2999, so it's actually 0.3, right, by rounding. So this is 0.8 total, and if you express this as percentage, this is 80%. And so, again, what did we say? The 100% rule says if the total percentage change, which we calculated it here, does not exceed 100%, right? So that's less than or equal 100%, right? We know the optimal solution, the old optimal solution will still be optimal, right? So, like we had in the first examples when we were changing just one coefficient and it was within the range of optimality or not exceeding allowable increase decrease. Now when we change more than one, if we calculate this percentage change, right, and this percentage change is no more than 100%, the old optimal solution will still be optimal, right? So now, given that this solution is still optimal, right, we just determined this in the first point, the second point here, right, we're using 100% rule. Given that this is still optimal, we can calculate the new optimal objective function value, right? The new optimal objective function value, but we need to plug in, right, the new optimal objective function value, but we need to change all the coefficients. So the first coefficient, we changed it to 400, so this is going to be 400, and the second coefficient, we changed it to 280, so 280, right? So this will be equal to 70,640, right? So the new profit will be exactly this. And alternatively, right, we can just determine how much will it, the objective function value, the optimal objective function value will increase or how much it will decrease. And right, because we increase one coefficient by 50, we could say that optimal objective function value will increase by 50 x1 star, right? So it will increase by, this is $6,100. Okay, but this is just for the increase by 50, and also with the decreasing by 20, the second coefficient, so, and decrease by right? By what? By 20 times x 2 star, which is equal to 1,560, right? So this is just determining the relative changes. If you take 66,100, add to it 6,100 and subtract 1,560, we should get exactly, right? You should get exactly 70,640. Hopefully this calculation is correct, right? So this is if we change two coefficients of the objective, and again, no other coefficients, nothing in the constraints has changed. And it happened that the total percentage change was less than 100%. We know the old optimal solution is still optimal, and now we can calculate the new optimal objective function value. So we know what happens to the optimal solution, it doesn't change, and what happens to the optimal objective function value, in this case, the net change is as an increase, right? Okay, here is a second question. What if the objective coefficient for the first variable increases to 400? So that's the same as before, increased by 50. But the objective coefficient for the second variable decreases to 260. Remember, it was 280 before. So again, I could say, are these individual changes within the allowable increase, decrease, or within the optimality ranges? And you will see they are, right? So this 400 is actually within this, or the 260 is within the second range. So I could say, right, that they are all within ranges of optimality, or the increases, decreases are not exceeding allowable increases, decreases. And again, as before, I can say that this is, however, insufficient to decide if the optimal solution will still be optimal, because we changed more than one coefficient, right? So each of those changes individually would not affect the optimal solution. The optimal solution would still be the same, but together, we don't know. We have to use the 100% rule. And I just a comment here. Of course, if this was, for example, 500, the increase would be by 150. I don't even have to use the 100% rule, right? Because just this change, 150, if this was 150 here and 500, right? This change on its own would be more than 100%. So of course, the 100% rule would already be violated, and we wouldn't have the same optimal solution. But now it's within, right? So again, applying the 100% rule for objective coefficients, right? Again, I have to do the increase over allowable increase, right? Plus decrease over allowable decrease, just because I'm increasing one coefficient and I'm decreasing the other coefficient, right? So you'd have to add all the increases and all the decreases that you apply divided by the corresponding allowable value, right? So in this case, it is 50 over 100, and in this case, the decrease is 40 over 66.67. And again, to calculate this is 0.5 plus, and in this case, this is 0.5999 something, so it's 0.6, right? And so that is equal to 1.1. So percentage-wise, it is actually 110%. And that is not less than or equal, right? That exceeds 100%, right? So if it exceeds 100%, so we know the old optimal solution might no longer be optimal, right? It might change, right? So as before, we don't know what if the optimal solution changes. We cannot recalculate the value of the optimal objective, the optimal objective function value. However, right, we know that the old optimal solution, right, the old optimal solution, 122.78, might no longer be optimal, but it is still feasible. If it is still feasible, therefore, then its optimal, not optimal, its objective function value, right? Its objective function value, which is now not 350 x1, but it is 400 x1, and this 300 we changed it to 280, 260, right? Its optimal objective function value, which is now 6980, right? This is a lower bound on the optimal objective function value, right? So just again to summarize, we don't know what the optimal objective function value will be exactly, right? However, we have at least one feasible solution, right? The old optimal solution is still feasible, right? So the solver can use this as the optimal solution, but it might change to another one that has a better profit, right? So under the new objective, 400 x1 and 260 x2. So we don't know what the new profit will be, but we for sure know it's not going to be less than this, because there is a solution that achieves this profit, and any feasible solution is a lower bound on the optimal objective function value when we're maximizing. So as before, whatever the change in the objective coefficients, we can determine a lower bound on the optimal value, provided that the objective is maximization. If the objective was minimization, there would be always an upper bound. And actually, there are other estimates that are possible, like if I would consider just part of those changes. Instead of increasing by 50, I would first increase by something less and make this change less than or equal to 100%. I could again estimate another bound, but I'm not going to go into details. At least we know the new profit will be minimum this.